Hi, my name is Crossling. I am an honors student at the Academy of Computer Science and Software Engineering. I'm doing my honors in computer science and AI. Today I will be presenting for you my project, Receptance-Based Attention, and I hope that you enjoy. So before I can explain to you what receptance-based attention is, I have to explain what attention is. So the definition of attention is an AI technique that allows models to focus on the most important parts of data. However, that doesn't really mean much. So let's put it in the context of a board meeting. Let's say you're sitting in a meeting and you're listening to somebody pitch something to you. You prioritize key points, like their sales numbers or their project updates, rather than every single detail of what they're talking about. This helps to focus on what's relevant and actually keeps you efficient and helps you make better decisions. And that's what we try to compute with attention. So how is that relevant to machine learning? Well, imagine you have a sequence of words. Those words individually don't mean much, but the second you compare each one of those words to every other word in that sequence, they begin to have meaning. And this mechanism is the mechanism that powers a lot of the back end behind large language models, such as ChatGPT or Gemini. Traditionally, attention is done using a mechanism called self-attention. So self-attention compares every word to every other word. Think about that. Every single word is compared to every other word. That is very slow and computationally complex. Receptance-based attention attempts to do this in a linear fashion. It compares the previous words that come before the current word that we're working with and uses a little bit of information from every single one of those previous words to compute the context of the current word. Here is a quick comparison of the computing speeds of both of these mechanisms. To demonstrate the power of receptance, I've created a small project just as a proof of concept that all it does is it takes in a function like a sine wave and converts it to a set of points. The points then act as the quote-unquote words in the sequence and are fed to the model, which then makes a prediction on the next quote-unquote word or the next point. Now, because I use a noisy sine function, it doesn't always predict the exact next point in the sine function, but as long as it falls between the two lines, the upper and the lower bound, which are just defined by the noise, we know that the model is performing correctly. So why did I use a noisy sine function and not just a regular sine function? Well, we need to remember that we're not trying to predict functions, we're trying to work with words. And words are also very noisy, because words have definitions. And some words can have multiple definitions, or can be used in multiple different places. For example, the word the can be used before dog and cat, or house. It has a very noisy relationship with all these words, but we do know that it falls before a noun. So with predicting within a range, we can then compute an understanding of where the token should be or where the next point should be, as opposed to its exact next position, which is useful in language modeling. So I've discussed predicting points on functions, but how does this apply to natural language processing? Like, yes, we understand we can predict the next point, but what can we actually do with this? It doesn't mean much quite yet. Well, we can apply this model to a language translation task by doing the exact same thing. We feed it an English sentence, which is the function that we feed it, and we ask it to produce for us the most likely next thing, i.e. the Afrikaans sentence. But hold on a second. You might be wondering to yourself, English sentences and Afrikaans sentences aren't series of points. They're not numbers, they're words, and they mean something in respect to one another, and they can only be computed sequentially, in other words, from beginning of the sentence to the end of the sentence. So how do we turn that into something that a computer can work with? Well, we do this with something called a tokenizer and an embedding space. So let's first discuss what exactly the tokenizer does. So we can't work with an entire English sentence at once, because how would we represent that as numbers? I mean, it's just a bunch of words that are strung together. Trying to put them all together over the thousands of different combinations, millions of different combinations that there could be of English words, would be a very challenging and slow task. Instead, we have to separate each one of these words. So this sounds fairly simple, but we need to remember that people, they put in their own jargon when they're writing sentences. And so we have to consider these things. We call these contractions. So because we are translating between English and Afrikaans in this project, we use a specific type of tokenizer known as a Moses tokenizer. Now, a Moses tokenizer handles contractions and is also specialized to handling Latin characters, which make up English and Afrikaans words. It separates each one of these words along white spaces and symbols. Now, obviously, this isn't very helpful because these are still just words, and words don't really mean much. But we can turn these into numbers now by expressing them as a vector, or another way of saying it is expressing it as a set of numbers that represent that word. We do this using an embedding space. Now, the embedding space's job is to map each word to an embedding, or a vector like mentioned before. It also allows us to update the embedding. That means that when we do our predictions of words, we can change the words to be closer to the words that we want over time. And so using this architecture, we can now not only feed a numeric representation to the model that can do predictions, but we can also update those embeddings for even more accurate predictions later on. So now we have each word represented in a sequence. We have the embeddings of each of the words. So we have our function. So now what we can do is we can take the embeddings of each of the words and pass them through the model. Now, by computing the difference between what we want from what the model is outputting, we can update how the model performs its calculations using something called backpropagation in order to get better and more accurate responses. So, as you can see here, I feed the model one word. Now, this word, over time, its pattern is learned, its embedding is learned, and it is shifted through backpropagation until it eventually settles on the correct prediction for the word. And as you can see, in the final output of the model, when I put in just that word, I get the correct Afrikaans translation at the end. Finally, we don't want to be doing this with just single words. Let's expand it. Let's try sentences. Why not multiple sentences? And that's where the power of this model comes in. Not only does it do its task in a quicker training time than a transformer model, but it can also successfully do translation. It should be noted that all parts of this project were programmed from scratch. That means that the function estimation model, the tokenizer, the embedding space, the receptance layer, including all the receptance layer components, as well as its built-in neural networks, were all programmed using only the NumPy library, which is just there to do matrix multiplication and simple linear algebra. This project is the very first implementation, at least that I've been able to find, of receptance-based attention, specifically the Ruwakov model. Not only can it do function optimization, as you saw before, but it can also do language translation. It does this in a linear time as opposed to a quadratic time, which is a time that most modern large language models use to perform self-attention. This means that the model is more scalable, meaning you need less computation to be able to do the same tasks. It also is faster at training and keeps all the benefits of self-attention and its output quality. Thank you very much for listening to my presentation. I really hope that you can see the quality in my project and that you learn something new. Thank you again. Have a good day.